All right, so now we're going to get into how to calculate quantum operations using mathematics. We've already seen the visual representation, and that's going to be adequate for the algorithms and examples we were using in this course. But in order to do general quantum computation, you need to do the mathematical calculations. So we're going to introduce that now. All right, and before I introduce that, I want to relate what we're doing to fractions. Remember when you learn fractions, let's say we have this problem. You have a pie to share with 3 friends. You cut it in 4 equal pieces, each of size 1/4. Your friend exclaims, "Just because there are 4 of us, it doesn't mean we need to eat the whole pie. I only want half that much." How much of the pie will you give your friend? Hopefully you recognize this as a multiplication problem, because 1/2 of 1/4, we know that when we say of, that means multiplication. And so we'll do 1/2 of 1/4, and we calculate that to be 1/8. We can also check to see if we were right. And when we cut these in half, we see, yes, when we cut those in half, there are now 8 equal sized pieces. And so it must be 1/8. Okay. So hopefully that by this point in your life, this makes sense. But I'm sure that when you were in 4th grade, I can't be positive about this, but this is not as intuitive as one might think, okay? Because we have these 1/4, 1/2, 1/8. It's arbitrary as to the fact that we put the numerator on top and the denominator on the bottom. And furthermore, why is it that for multiplying, we multiply both the numerator and denominator? But if we are adding, we have to first make the denominators the same, and then we add only the numerators. These seem, if we don't have an understanding of how this works as a whole, then it just doesn't make sense. So when we're thinking about how someone came up with what are the rules behind fraction multiplication and what are the rules behind fraction addition, what they did was they looked at a real problem and they looked at what the real operation would do in real life, separate from these numbers. And then they looked at the mathematical representation and they figured out what mathematics gets us the right answer, not just for this problem, but for every problem. And so it is often the case that if you just look at the mathematics and what you're trying to do, it doesn't make sense on its own. We just have to trust that someone has figured out that this always works. And we could go through all of the mathematical proofs that show that. We're not going to in this class. We want to learn how to do these things. But certainly, if you want to become someone who creates quantum algorithms, you will also have to learn how to prove things, because then you'll be doing things that no one can check. And if no one can check them, then you need to prove they're correct on the mathematics. But we're not going to be doing that in this class. Okay, so let's look at addition and multiplication, right? Just to emphasize how natural it is, hopefully, to us now, but how it really doesn't make sense. For example, when we're adding with same denominators, we add the numerators, but we make no change to the denominator. When we're adding with different denominators, we have to first multiply the 2 denominators together if there's no greatest common factor. And then we multiply the opposite. We do ay plus bx. Like, all of this just seems counterintuitive until you look at the full drawn out example and you understand why. Okay? And then for multiplication, we just straight multiply the top 2 and multiply the bottom 2. We will see that matrix, if we look at what we're learning today, it has the strongest correlation with addition with different denominators in terms of the sort of complexity of the actual mathematics we're doing. Okay, so the whole point of this was just to point out that fraction multiplication is easier than fraction addition, even though multiplication of integers is actually harder than addition of integers. All right, so what we want to learn is a mathematical calculation to calculate the NOT gate. Okay, and what do we have? We have bracket notation, we have vector notation. Okay, and we already learned that the whole point of vector notation was to be able to do operations. So it's going to be no surprise that we are going to use vector notation for this. Okay? And so we remember that in the general case, it's A over B, and then the not operation flips it to B over A. Okay, so we want to figure out how this works, and we want to figure out how it works not only for a not gate, but for any arbitrary gate. Okay? So for this, we need to introduce a matrix. A matrix is values laid out in a grid, similar to a spreadsheet. A spreadsheet is a giant matrix. Okay? So let's say I have a grid of numbers, and these numbers happen to represent each row is a student and each column is an assignment. And so these numbers are not placed randomly. Their position in the row and column ties them to a specific student and assignment. And so this is how matrices work. And so we have the matrix symbol. Notice that that's the same as the vector symbol. It's merely that the vectors are one-dimensional. It's just a column, or you can write them in a row instead, but it's just a single line of numbers, whereas a matrix is a 2x2 grid. Okay? And the other thing about the matrix is that we take off the labels. So we just see the numbers, and if this were a spreadsheet, those labels are just for humans, but for the computer, it's just the numbers. All right, so let's see how this relates to quantum. In quantum, every gate is represented as a matrix. Why? Because the mathematics works out. Luckily, Einstein and others figured out the mathematics, and we didn't have to. All right, so let's look at how this works. We start out, we need to learn an operation. This is called matrix multiplication. And now you can see why I related it to the fractions, because we have the sum of products. So we have a matrix and a vector. The width of the matrix needs to be identical to the height of the vector, because what we do is we go across each row of the matrix and the vector, and we start with the first, the leftmost item in the row and the topmost item in the vector, and we multiply those. And then we go into the next one, B and Y, and we multiply those, and then we sum those products. Okay? And then we move down to the next row in the vector, in the matrix, sorry, and we repeat on the vector. So we go down to the vector every time, but we're using a different row each time. And the result vector, it sort of seems like it might be a matrix because I see 4 items there, but notice that the top one is a mathematical calculation, which will result in a single term. So I do the 2 multiplications, and then I add up the result, and I get a single number. So my result will be a vector and not a matrix. All right, so what are these? Well, the leftmost one is the quantum gate. The matrix is the quantum gate. And then we have the initial value of the qubit in vector notation, the state of the qubit. And then when we calculate it, we will get the end state, the resulting qubit. And if we wanted, we could put that back in bracket notation if we find that easier to read. Let's try it. Let's try it with a not operation. So I start out with a 1, a black ball in my not. So my initial vector is 0% probability of a 0 and 100% of a 1. And so that's a 0 on top and a 1 on the bottom. And then I put in my not operator. I put it to the left. And so now I have these. And then I make my calculation. So I do the first row, 0 times 0 plus 1 times 1. And then I go down to the second row of my matrix and do that again with my same vector. So 1 times 0 plus 0 times 1. And I get a 1 on top and a 0 on the bottom. And that is exactly what I expected. I expected to get a 0. Likewise, we can take this initial vector of a 0 with a 1 on top and a 0 on the bottom, take my same not operator, and do the same operation. And I get the 0 on top and the 1 on the bottom. Feel free to pause this. You can go through it yourself if you need more time. Then we get black as the result. All right, so now let's take something a little bit more complicated. Let's take the case where I have a single white ball and 3 black balls, which is a 1/4 probability of the white and 3/4 probability of the black, which when you take the square root of that is 1/2 and √3/2. Okay. I invite you to pause now, write out the matrix and the vector, and go ahead and try to figure out the result on your own. And then you can check your work, and if you got anything wrong, then you can see the video. So first we have to set it up correctly. We need to remember to put the not operator on the left and the initial vector on the right. And then we're ready to make our calculation. So we remember to do each row separately, and then we can calculate our values. And we get √3/2 on top and 1/2 on the bottom. All right, let's try the H operator. So once again, we get our initial vectors. Again, I invite you to pause and try to do this yourself now that you've been introduced to the H operator. In fact, now if you look up on the internet for the operator for a quantum gate, then you would be able to do any of the quantum operations. All right, so then we multiply this out. And we have our expected results. And you see that that negative sign in the bottom right-hand corner is what gives you the negative sign when you're coming from a 1, from a black ball. We can do this again with the white ball, and what we'll notice is that that negative sign gets, the negative 1 gets multiplied with a 0, and that's why there's no negative sign when we start out with a 0 ball. And I want to emphasize how important it is for you to try these on your own before just letting the video skate through, because it's deceptively simple to watch mathematics go by on the screen and think that you could do it yourself. But it's really important that you actually do it yourself so that you can check, can I do it myself? Am I going to remember to put the vector and the operator on the right side? Am I going to remember how to do all these calculations? So make sure that you're doing at least some of these on your own, just to try it. Okay, so what did we learn in this video? A matrix is a two-dimensional grid of numbers in which position is important. It matters. It's used in many, many things, but in quantum, it's used for qubit operations, and those operators are stored as their own unique matrix. So each operator has a matrix. And matrix multiplication is used to calculate the output of a quantum operation. And today you learned how matrix multiplication works.